Okay, good afternoon, everybody. Thanks for joining us on the second day of this research symposium. We are going to be beginning with our program for session 3. We have had a couple of modifications since yesterday, which have been reflected here on the title screen. At this stage, we're very pleased to go ahead with the presentation from Dr. Tao and look forward to hearing her research and findings. So without further delay, I think we'll go right ahead with that. Dr. Tao, can you take over the screen?
Thank you very much, Matthew, for a nice introduction. I will share my screen now. Can you see my screen now?
Yep, it's coming through, just in presentation mode, and you're ready to go.
Okay. First of all, thank you very much for giving me an opportunity to share our research work. It is an assessment of annual mortality attributable to ambient PM2.5 in Bangkok, Thailand. I am Thao Pham, and I'm from the Joy Road School of Energy and Environment, King Mongkut University of Technology, Thonburi, Bangkok, Thailand. And the result that shared in this presentation is an extract from a publication that we have published last year as the same title, and it is the collaboration between the University of North Carolina, US, with King Mongkut University on an exchange program, and the journal has been published in open access, so it can be downloaded. For further information, I would like to start my presentation. We give you update on the global burden disease in 2019. And according to the source, the State of Global Air Report 2020, air pollutions, including ozone, PM2.5 and PM10 is combined is ranked the 4th leading risk factor for death globally with the number 6.7 million. And when we look at regional views, there is the reason for some regions, for example, the European but a high income, and also not the Latin America, but there is still an increasing and less progress for some regions such as Southeast Asia, East Asia, and Oceania. There's still a high share and increasing trends of impact of death attributable to PM2.5. Back to air quality situation in Thailand, currently there is 2 major problems with ozone and PM2.5. And it's been well known that it had been occurred mostly during November to March. It is the dry season of the country. And we have observed that there is an exceedance of national standards occur in Bangkok metropolitan regions as well as the northern part. And here is some news from the media during the period to gain the awareness from the also the community, and it's mostly see there is a observe and record for Bangkok and also in Chiang Mai. So our team have collect information of PM2.5 measurement in Bangkok during 2012 to 2019. 18. We start with 2012 because this is the year that there is a monitor of PM2.5. And at that time, there was just 1 station. And to 2018, the time that we conduct the study is 10 stations. And up to now, most of the station in Bangkok and Thailand has been monitor PM2.5. And when look at the data, we observe that firstly, the missing data has been observed in 2012 12 up to 90%, and the situation is better recent year. And also the annual mean, we see that the annual concentration of PM2.5 had been decreased and moved toward the national standard, which is 25 microgram per cubic meter. However, we still observe that there are still episodes, mostly during the dry seasons, that a number of exceedance had been observed, mostly for January, February, March, and also sometime in the end of the year. To give more information on how air pollution affects health, we have the emission. Here we can see the industry, but actually it's come from several sources. And the second picture here is, we can see this is the human hair, and it's already small compared with the fine percent that normally we cannot see clearly with the human eyes. And the blue dot here is indicate PM10 and PM2.5 even very small. And the scientist has been confirmed that PM2.5 can give also adverse effect to human health and some diseases such as short-term cardiovascular, respiratory, or long-term disease such as lung cancer or stroke as well. And the research objective of our team is to generate missing PM2.5 data by interpolate the existing PM2.5 and PM10 data and to determine the daily PM2.5 and PM10 ratio. And with this, we can get the more complete data set of PM2.5. And we identify the relative risk and to resulting concentration response coefficient. This is the relationship between PM concentration with some health endpoint, and here we apply the mortalities of cardiopulmonary lung cancer mortalities as well as the all-cause non-accidental. And finally, we determine the annual mortality attribute to PM2.5 pollutions utilizing band map community editions. And in the last objective, we also compare different data set from US and China as well as Thailand. The workflow of the study, we start with the estimating, like we collect PM the data and then have to pass the QA/QC to check the missing data, and to check the paper, there is some criteria for us to include the data. For example, the missing should not be like we need to have the data cover more than 7 to 75% in order to include in the analysis. And once we have PM2.5, PM10 ratio, we calculate the daily ratio and interpolate that to estimate PM2.5 concentrations. Then with the mortality, we can estimate the so-called beta value. It is the relationship between mortality and PM2.5 concentration. Together with population, we input to band map CE. This is a tool and to estimate the health burden and health benefit under some scenario that if the air quality in Thailand had been at meet national standard as well as the WHO standard. This is one that we result of the first objective. The gray color is PM10 and the orange color is PM2.5, the data that we collect from Pollution Control Department. The green color is the interpolate one. So, and also above here, we can also estimate the ratio of PM2.5 and PM10. Once we do this work, we have the validations we use tenfold cross-validation and to run the data utilizing 90-10 model, where only first 90% of the data were trained, and then the residual 10% was tested using the generate PM2.5 and PM10 ratio. This is the result, and then we obtain the complete data set for PM2.5 back to 2012. And we have input the data to BandMap. BandMap full name is Benefit Mapping and Analysis Program. This is the software. The tool has been developed by US EPA, and it is a geographic information system-based tool to estimate health impact resulting from air pollution, and was used to determine the link between PM2.5 concentration and mortality. Here is the key equations and the information to input in BandMap, including pollutant chains. Here we see delta PM, but it can be delta ozone or any pollutants of interest, together with the populations and the baseline incidence. Here is mean the number of mortality and morbidity in the areas of interest, and together with the effect estimate, is the relationship between PM2.5 and the mortalities. We can calculate the health impact. And this software is open access, and it can be downloaded from the website USCPA. The data input in BandMap, according to the equation, is we kept the populations, and the population is available in Thailand from National Statistical Office. It's by province, by gender, by age, by socio-economic. For ambient air concentration, we obtain hourly concentration from Pollution Control Department, and actually currently there is another data set from Bangkok metropolitan region as well. And for health data, we obtain from Ministry of Public Health. For health impact functions, there is also from literature review that we include from the case of US and China, as well as self-developed in our research. Initially, we have the comparisons using Bangkok dataset with the beta value from US and also from China, and we see there is a difference. So the mortality, avoided mortality associated with ambient PM2.5 concentration from 10 microgram per cubic meter reductions. From if using the US data, we observe that there is 7 times higher for non-accidental, 5 times higher for cardiopulmonary, and 4 times higher for lung cancer when compared to the case of China. So in this case, we also estimate relationship between mortality and PM2.5 concentration using Bangkok data, and we found that the results suggest that the population in Bangkok and China is quite similar, affected by the same PM2.5 exposure, and were different from the US population. This is well in line with the literature review to see that there is the regional difference of the relationship between mortality and PM2.5 concentration, considering the different geographical, social, economic lifestyle as well. And at the end, we apply our estimate of Bangkok beta to input in BandMap, and this is the result. We found that PM2.5 concentration in Bangkok contribute to more than 4,000 non-accidental and around 1,300 cardiopulmonary and up to 400 lung cancer mortalities annually. We also investigate the case that what if PM2.5 in Bangkok is well under Thai standard? What is the benefit of health? And we found that attainment of PM2.5 level to national standard would reduce the annual premature mortality in Bangkok by 33%. And once the country can meet that, and if we go further to WHO standard, the benefit could up to 75%. And this is the summaries of the research. Is we have interpolating PM2.5 data based on the seasonality and daily concentration change in PM2.5 and PM10. Mostly from literature review, the annual ratio has been suggested, but actually there is variations seasonally. So we have observed that and would like to calculate that to have the complete and better data set of PM2.5 and back to historical in 2012 as well. After that, we have linked the annual mortality and PM2.5 in Bangkok and to see the relationship and also able to compare that with some literature review from US and China and how mortality burden associated to PM2.5 concentration in Bangkok had been quantified and also highlight the benefit of attainment of PM2.5 level to more stringent standards, firstly to national standard and secondly to WHO guidelines. Way forward is we are working to extend the study area to cover Thailand in provincial scale with most recent data. Currently, PM2.5 monitoring station has been well established over Thailand, and also health mortality and morbidity endpoint has been well organized as well. So this is something that for us to move forward. And the next step, we also want to quantify the economic impact from health burden in order to give a message that to policymakers as well. And this is also one of the important components for cost benefits analysis to investigate the most effective control measures. And finally, what we are also working on is to develop a Thai band map CE. Like we build in the band map data with Thai and also provide a training band map CE to Thai community so that this tool can be used for both academically and also in the officer in the provincial scale as well. And finally, thank you for your attention. And here I would like to say health isn't everything, but without it, everything else is nothing. And once again, thank you, and questions are welcome. And for further information, you feel free to contact me. Thank you very much. And back to you.
Thanks very much, Dr. Tao, for this presentation and for keeping to the time. This is really very rich and insightful. I'd like to zero in from the side of the Secretariat on a couple of the key findings here. In particular, the apparent divergence in the Thai data in comparison to the standard models that are used elsewhere. In understanding this issue, we heard yesterday from Kun Siwat and others that when examining the PM2.5 particles for their toxic equivalencies, particularly around polycyclic aromatic hydrocarbons, that we do see very significant differences in the composition of the PM2.5 pollution at this level. Therefore, with this basis in mind, I'd like to ask for your view on whether or not you believe the toxic equivalency models could be the explanation for the divergence that we're seeing here in the mortality projections from the models outside the region when they're applied to the Thai data.
Yes, thank you for the questions. I think different regions will have different signature source, and with that we have observed the different response from the mortality and toward to concentration in different area. And I also think that is because of some unconventional source in emerging cities that should be also be a key contribution to that.
Great, thanks very much for that. And we certainly take note of these recommendations. I think the development of a Thai BenMat model based on local data sources and profiles would be extremely valuable. So thank you very much for that. I'd like to open the floor briefly for any questions for the audience for Dr. Tao. And then Vinayak, if you can be prepared to take the floor. Okay, great. With no hands coming up from the floor, let's proceed now to our second presentation, which will really drill into an innovative perspective on how to understand the urban traffic flows and their role in air pollution as focused on Bangkok. So Vinayak, over to you.
Thank you, Matthew. Thank you all for this opportunity. I'm actually speaking on behalf of Divya. Divya is a lecturer at UNSW. She's finalizing her course. There's an exam. Literally, she's proctoring right now. I'd like to have the opportunity to speak on our behalf. So what I'll be talking about is crowdsourced traffic data and its uses specifically, and I'll drill down specifically in its application for being able to actually predict pollutions and pollution levels. So with that, it's actually based on two papers I'll be discussing. Both are published in open source journals in +1. One is characterizing multi-city urban traffic data, so in collaboration again, Divya and myself. And the second one is a simple.
Vinayak, we are losing your audio. Is there anything that you could do to boost your audio quality?
All right. Let me try one thing. Sorry. Hi. Is it better now?
Yes, that seems to be working for now. Let's go ahead on that basis.
All right, perfect. If it gets worse, then I'll just I'll switch off my video. Essentially, it's based on two papers which are in open source journals. One is characterizing multi-city urban traffic, and the second one is simple crowdsourced traffic, delay-based traffic. So the first one uses crowdsourced data to characterize congestion and congestion indices and its implications on various things. But one particular thing of interest here is in pollution levels. The second one is actually using the same data set to do real-time traffic management to reduce emissions and improve safety and delays. So I'll talk about both of them fairly quickly. So one of the things that has happened when we started, and this is probably over the last 5-6 years, it has been the emergence of crowdsourced data. So even now, a lot of the ITS is based on fixed physical sensors, either based on camera or loop detectors, the one down here, the loop detectors or the cameras. Now, with the prevalence of mobile phones and everybody having a mobile phone with themselves, there's a lot of that data around speed, locations that are actually being aggregated. So in particularly, what of interest in Bangkok and Thailand is also the fact that there's real-time GPS data from taxis that are coming through, which are going to be very useful. So I'll talk about that in a bit. So this data has been useful from various standpoints. So what you can actually see is in real time, you can see the colors changing. So this is kind of a real-time congestion index changing, and this is based on actually Longdo data, which we have been capturing and then pulling and then analyzing on top of that. So essentially, this data set gives a large, so it's very scalable. It is available pretty much at scale, and it also provides a lot of insights into origin destination travel, into congestion indices, speeds, and acceleration and delays, etc., depending on the granularity of the data. So for the first paper, which was around characterizing multi-city conditions, what we did was around, we took a large number of cities across the world, and we were able to characterize their, create an index, something called a congestion index, which which was based on the free flow speed and how long, or what is the area over which over an entire day, over which um, the speeds or the delays are exist. So it's basically delay into the time, and based on that, we actually characterized and ranked them. It also provided us with some really interesting insights about spatial dispersion of congestion, also around temporal dispersion of congestion. So what is travel time reliability and aspects of that, which are more useful for understanding congestion and congestion indices. The other aspect, which is also very, very interesting, is different cities have different characteristics. Basically, we were able to, there are like 4 types of congestion patterns in formation and dissipation. So across the various cities, we were able to cluster them into 4 types. So one is you have a clear peaks. The morning peaks are quite high. The other ones are much flatter, and they tend to be coming out of India. They tend to be flatter, but you have peaks, but tend to be quite flat. And then there are other characteristics in terms of how many peaks are happening, etc. So the one thing which is particularly interesting from the context of emissions is once we characterized congestion indices of these cities, we were able to characterize, compare it and correlate it with different factors, like factors such as population density, GDP per capita, PM 2.5 and PM 10 data sets, which some of the cities were actually publishing. And we found a really high correlation, in fact, when we estimated the coefficients and did a regression model, it was quite high in terms of the correlation with the PM 2.5 and PM 10. So congestion index had a very strong correlation there. We also then, so this graph here on the bottom here on the right actually ranks the congestion index and the dispersion. So it tells you what is the mean congestion index and the distribution of that congestion index. So as the congestion index actually increases, what you find is there's a larger distribution in the congestion observed. So yeah, that's essentially what that initial paper was found. So in collaboration with Divya, Matthew, thank you for the opportunity as well on this. What we did was we started kind of analyzing data from Bangkok. So the first thing we did was we realized that so our initial analysis was based on Google and TomTom data, and to actually collect that data, it's quite expensive, like even to pull that data. Fortunately, we came across long-door traffic data, so it is openly available and it's extremely useful. And most importantly, as a researcher, and for doing a project for public good, having this free has been extremely useful. And I wish more cities and more countries could do that, is provide those kind of data sets. So the first thing we did was we went back and we compared the congestion indices, which we would actually pull out of the long-door data with that of the Google congestion index, which we had produced for the same time period, and we found a very nice and strong correlation between them. So that was very positive. So that means that the long-door data was very useful to kind of take forward. Then, based on 2 days data, so this was our preliminary analysis and preliminary results. We are actually collating this to kind of create a new, develop a paper. We found initial results suggested and this was based on a couple of days of data. We found some strong correlations with nitrogen dioxide, PM10, PM2.5. and we found literally no correlation with ozone, sulfur dioxide, and carbon monoxide. And this could be because of multiple reasons, right? So this was, first of all, it was for a couple of days. The other reason is there's a lot of impact of rain, wind, and environmental factors as well. So what we did was we took almost 6 years of data, and we have started kind of looking at selectively analyzing and controlling for weather with no wind and rain, and looking at just being able to isolate isolate the impact of traffic, because there's a lot happening, especially with the burning in particular season. So if you try to take the whole data set across, there's a lot of confounding factors. So the initial results are suggesting that, at least for carbon monoxide here, there seems to be, and the nice thing is we were kind of comparing it based on the traffic trends as well. So there seems to be high correlation at around 9 a.m. So 9 a.m. Is roughly when you have the traffic peak as well, like when traffic starts beginning. We find that there's a high correlation at 9 a.m., almost 0.5 across different stations, a wide variety of stations for carbon monoxide. We find that there is a bit of a delayed lag in correlations with both PM 2.5 and PM 10. We see that across the data sets, and we see similar results coming out in the evening as well. Now, there's more research to be done, and we are employing different statistical methods to kind of characterize this, because there's a lot of environmental factors that are playing around in this space. So what we did was that we know that, so there are a couple of things we know. So one is we know for a fact, at least from controlled laboratory studies, that we know that that vehicle delays and vehicle congestion actually are a big contributor to pollution. The fact that you have wind, rain, and environmental factors that might be moving it across spatially and geographically, but still they contribute fairly quite a lot. So what are the mechanisms we can use to actually reduce those emission profiles? And one simple one is traffic signal control. So the idea was can we use this congestion data, like the crowdsourced data, to actually control traffic signals in real time? The whole value of using real-time crowdsourced data was that you do not have to make any investments, capital investments on sensors. You do not need loop detectors. You don't need cameras. You can get this data pretty much real time. So it's almost democratization of crowdsourced data. So it's data from the people, and now it's going back to contribute and improve the lives of the people. So we developed a novel algorithm based on max pressure, and we trialed this across several cities. So they include cities in India, 3 cities in India, 2 cities in Indonesia, and also as well as Muscat. And what we found was anywhere between 14 to 28% improvement in delays. So we were able to reduce delays in that range. So essentially what we found was that these such crowdsourced traffic signal controls can, first of all, they're quite robust, because they don't get affected by weather conditions and adverse, because it's crowdsourced data. So those data if your mobile phone is working, that data is being generated. So it's very cost effective from a capital standpoint and from a maintenance standpoint as well. And we were able to find delay reductions of approximately 20% across different parts of the world where we've done. We in one particular location we did we were actually evaluated emission impacts, and we were able to see that the emissions reduced by approximately 8%. So by just deploying that, and other studies have shown that adaptive traffic signal systems can improve traffic safety by 18%. So in general, we found that this is a really cost-effective way when you don't have enough budget, you can actually use such a simple model to help reduce emissions and improve customer mobility impacts. I can go through some of the case studies, particular case studies, but I'll be really quick. So we again did a validation of data between the crowdsourced Google and real time, and we found a good fit. Again, here we found improvements in the Indonesian by anywhere from 17.5 to 27%. We deployed this in Mumbai, and one of the things we found was that because you can now coordinate the signals between two traffic signals, we were actually able to remove the evening congestion peak. So it was just because that they were not timed properly, that you didn't have a proper coordination between the signals, that you're having this congestion in the evening. So we were able to reduce that. And with that, I will stop. So thank you so much. Hopefully I was within time.
A little bit over, but I think it was worth it. Very, very helpful. I think there's really exciting ties to tangible interventions here, and obviously vehicular traffic is a very common problem across the region. So it's good to see such an innovative solution that's delivering real results. I would like to ask what you would identify as the capacity gaps for adoption of systems like this in mid-sized urban areas in Southeast Asia. What are the obstacles for moving forward?
So the main obstacles would be just the buy-in. First of all, I think one is just from a bureaucracy and a coordination standpoint, it's never clear who owns the traffic signals. Is it the municipal corporation or the traffic police? So there is a bit of my personal experience has been there's a lot of bureaucratic coordination and stakeholder engagement required around that in terms of ownership and then uptake. The second one, actually, I forgot to mention is that we also demonstrated that because you have this adaptive traffic signal controller, we interviewed traffic policemen. So now you do not need a traffic police kind of directing the traffic at these locations. So there has been health benefits for the traffic policemen on the ground as well, which the interviews had actually pointed out. The second one is, I think, just creating. So that currently, there's another perception which is happening is that any smart traffic signal systems require physical sensors, and a lot of them have used camera-based systems and loop detectors, and they don't really work in conditions like in Southeast Asia generally. So I think there's a bit of confidence building and trials that require to be done, I think. So those are.
Okay, great. Thanks very much. I think that's quite helpful. I'm going to request control on the camera because I'm actually the next speaker for this session. But while we're switching the presentation over, since I know that this is a common issue for all of us, let's open the floor for anyone who would like to ask any questions on this tool for reducing vehicle emissions.
Thank you all. Thank you, Matthew. And thank you from Divya as well. She sends her apologies. Thank you.
Okay, great. No problem. All right, hopefully we've got the right material on the screen now. Ariel, can you confirm that the presentation is showing?
Yes, it's showing.
Yes.
Great, thanks so much. Okay, so we're going to switch gears slightly to be linking on the air pollution and health dimension. We had a lot of really good content on this yesterday. So for this portion of our program, I'm going to focus specifically on the work that ESCAP is doing around areas in air pollution and public health, particularly on gender, that have not yet been spoken to. So part of this is our effort to solicit feedback and peer review from this body of experts. In contrast to the papers we've had so far, the purpose of this symposium is to solicit peer review and constructive feedback on the work that we have here and the findings that we are moving forward with. So please don't hesitate to put your hand up for any observations that you may have. So in an effort to keep myself onto the time schedule, I'll start in with a brief description that for this presentation and as well in session 4, we're going to be demonstrating results that we've obtained through the data warehousing exercise that ESCAP has undertaken on air pollution in the region, particularly for Thailand, and specifically in this case, Chiang Mai. So we're very fortunate to have had very generous support from the side of the Thai government and the provision of data sets across multiple ministries, which has really allowed us to come up with some innovative findings in this space. I'll go more into detail on the underpinnings of our model in the presentation in session 4, but for this content, we're going to focus specifically on what we've done with public health. This is intended to be a complement to the work presented by IHPP yesterday. So for our efforts in this case, we're focusing specifically on cause of death and inpatient data because these data sets allowed us to make a gender-sensitive analysis, which is a key priority for our efforts. In order to factor in the links between air pollution, PM2.5 exposure, and public health, we've attempted to normalize the A and B control sets through regional groupings, which I've displayed here on the screen. This becomes our dimension for factoring in the PM2.5 exposure. We've created these regional aggregates for the north, northeast, Greater Bangkok, Central, and Southern regions. And these are the factors that I'll be referring to throughout the rest of this presentation. Obviously, for health outcomes, there are a number of collinearities and exogenous factors that impact how to properly model and understand this. One of the most significant of these is, of course, household income. In order to do that, this is a brief visual synopsis of how we have conducted a peering exercise to make sure that we were comparing data sets that had statistically similar levels of per capita income among and between in order to accommodate this factor. In these matters, we have also made the decision at this stage to omit the Greater Bangkok region from the analysis because of the significant income disparities and the prevalence of private hospitals in that particular area. So the analysis that you'll see following this puts Bangkok out of the scope. In order to examine these findings, we've used the linear model in order to determine where we're seeing correlations in the factors. Because of the complexities in linking together the number of data sets necessary for this type of analysis, we have used yearly pollution values and averages for the modeling. This has been statistically significant in the data that I'm about to show you, but is notably different from the work that we've done on air pollution causality, in which we were able to model the impact of policy activity on predicted outcomes. For the health data, we've taken this to correlations. We've heard very extensively on the issues of lung disease in the presentations on mortality attributable to PM2.5. So for this presentation, I'm only going to touch on that topic lightly. This is a summary of some of the findings that we've had in our studies of those particular conditions. In the data that we have available on this, we do see that there is a significantly higher lung cancer rate in females in the northern provincial groupings of the country than in the south. Even when accommodating for factors such as smoking and other lifestyle factors, this variance remains very clear in the data. We've therefore identifying lung cancer risk as one of the health conditions that has a strong gender correlation in the data for Thailand. Moving beyond the traditional effects that we see in the mortality studies, speaking generally, we are very intrigued by the data that we've seen in a specific analysis on the topic of birth defects and air pollution. I'm going to go through the methodology that we've used with that and summarize our recommendations now. Just for reference for the group, the conditions that you're going to see and the data that we have to display for you are with reference to the ICD-10 disease classification codes. These are some of the categorical breakdowns for those, particularly around the birth defect condition. So this is a reference slide. In the summary of our findings, we are seeing birth defects in consistently higher rates in the north, northeast, and central provincial groups than in the south. This tracks proportionally to the levels of PM2.5 exposure that are reported in these ecosystems and appears to show a statistically significant correlation that cannot be explained by other factors. Some specific examples of the ICD-10 codes in which we are seeing those pollution correlated spikes include things like hemolytic diseases of the fetus and newborns, as well as a variety of other birth defect conditions, which I'll go into now. So this is one particular slide to illustrate the degree of variance that we're seeing in this group of conditions, congenital malformations in the nervous system among fetuses, and the presence of intrauterine hypoxia for both male and female infants is obviously statistically quite significant. The data does scale with the PM2.5 exposure and is within the predicted levels for the bulk of published research on the effect of air pollution on pregnant women and newborn children. So this is obviously very tragic numbers, and we believe certainly worthy of extensive consideration in the future analysis of burden of disease of air pollution in Thailand. When we talk about correlation, causation, and relationships, I'd like to use this slide as an example of the ongoing research analysis that we are doing. In this particular case, we're using the range of conditions originating in the perinatal period with these ICD-10 codes. And you can see here in both the data and the visualized scatter plot, what we're seeing emerge when we use a machine learning statistical analysis on these data sets. Obviously, in these cases, we've highlighted the exposure to average PM2.5 number, which has a statistically significant relationship showing up in the Pearson's coefficient and so forth, showing the scaling of these conditions and their impact on women and pregnancies within the Thai data here. So within this context, it's obviously a very tragic and problematic finding that I think speaks very clearly for itself on the need to include these gender-related aspects to the impact of a burden of disease of air pollution in the country and in the region. So from our perspective, based on the data that we've seen in our analysis so far, we are detecting a strong correlation with specific conditions in the perinatal period, including birth defects that correlates very strongly with PM2.5 exposure. This is consistent with the research in the area and provides a strong ground truthing exercise to the predictive models. We expect to undertake a significant amount of future work on this particular dimension in order to be able to help target air pollution policy remediation in reaching out to the people who are most affected by PM2.5 exposure to be able to reduce the impact of air pollution from this gender and public health perspective. So thank you very much for your attention to this presentation. Definitely going to open the floor for questions. If it's the consensus of this group that these findings appear robust, then we'll just denote that in the record. But if anyone has any concerns to express on the nature of our analysis, please do so now. Otherwise, we will go ahead and proceed forward into the fourth session of our program. Great, Dr. Pam, I see you have your hand up. Please proceed.
Thank you for the presentation. It's very nice information. I just have one curious for the number of lung cancer in female in the north. Is that related to also the indoor particulate matter as well? Because for some case, if they use the wood or something, charcoal, it may also impact. Thank you.
Great. Yes. Thanks for this this question and observation. Absolutely. You know, the impact of indoor air pollution exposure issues is well established in the literature. At this stage, indoor air pollution is an area in which we hope to expand our analysis in the coming months and years. The proxy values for PM2.5 exposure in this case are outdoor air pollution. So we look forward to bringing in those factors as well. Dr. Kim, I see you have your hand up. The floor is yours. Please proceed.
Yes, thank you. Thank you, Matt. My question or my concern is in the chart showing the linear correlation between the birth defects and average PM2.5. So that is how you come with that average PM2.5? You have the slide. Can you show it back?
Yes, great. Let me get the slide up for reference so we can have that visual. Okay, I hope that is now displaying properly on the screen.
So
I think you're referring specifically.
Yeah. How you come up with that average value? It's so positive, but to me, R squared too high. We say it's 0.83.
Yeah, so the average PM2.5 exposure, I'll have significantly more technical details on that in the presentation for session 4 and how we've built out our air pollution model, but just very briefly to answer your question now, that's the aggregate PM2.5 level for the provincial groups that I had on the earlier slide, showing how we had grouped the provinces into the 5 categories. So it's the average for the provincial group of that region.
Yes, thank you. I will look forward to another presentation. Thank you.
Okay, great, thanks. Happy to provide further data. Okay, so thanks very much for that that feedback. I think at this stage we're pretty close to on time to conclude session 3, and we have quite a packed session 4. So let's then go ahead into the next session here. Okay, so our first speaker for session 4, which is going to focus on the exploration of opportunities and gaps, will be Hannah Klauber, speaking to us on the effect of thermal inversion, air pollution, and COVID-19. Hannah, can you go ahead and take the screen?
Yes, thank you very much. I will try to share. 1 second. Now you should be seeing my screen.
We do, yes, please proceed.
Perfect. So thank you very much for the invitation, and good afternoon, everyone. My name is Hannah Klauber. I'm a researcher at the MacArthur Research Institute on Global Commons and Climate Change in Berlin, which is a scientific institute focusing on providing social science and economic analysis. And today I will present a paper written together with my colleagues Sebastian Kraus and Nicolas Koch, also from MCC. And in this paper, we analyze the causal effect of air pollution on COVID-19 case numbers and death numbers. So I will start by giving you a short introduction to the research context. Obviously, we all know that both COVID-19 and air pollution have a direct effect on human health. There's extensive literature on the adverse effects of air pollution on human health, and we have all witnessed the health-harming effects of the COVID-19 virus. Now, early in the pandemic, the interlinkages between these two health threats have been discussed. We have observed that in response to COVID-19 policies such as travel bans or lockdowns, air pollution levels have decreased, as can be seen here for China when looking at the nitrogen dioxide levels. And there are studies that have assessed the health effects of these pollution reductions. Now, there's also a link the other way around. Air pollution affects the health impacts of the COVID virus. Long-term air pollution exposure leads to several preconditions, such as respiratory diseases and cardiovascular diseases that exacerbate the course of a COVID-19 infection. And in addition, short-term air pollution exposure also leads to inflammatory reactions and lower immune responses that can make new infections more severe. And these short-term pollution effects on COVID-19 infections are the effects that we are interested in our paper. And we are not the first to look at these effects. There are actually several studies that have demonstrated an association between short-term pollution exposure and COVID-19 outcomes. But to our knowledge, there are only 3 quasi-experimental studies, so studies that are really focused on identifying a causal link and not just an association. And these 3 studies have looked at individual countries. 2 have focused on the US, 1 has focused on Germany. And we want to add to this literature by providing first cross-country evidence. So I will briefly describe the methodological challenge to then explain how we use remote sensing data, weather data to overcome this methodological challenge of identifying a causal effect. The problem is that air pollution is not randomly assigned to places, but results from different dimensions of human behavior, and we cannot always measure these dimensions. 2 issues that may arise are illustrated here, and I'm sure everyone in this audience is very familiar with these issues. In the specific context of our research, we have to, for instance, consider that the pandemic affects human behavior. It affects how populations move, it affects mobility, and this in turn affects air pollution levels. So there's a reverse causality that we have to take into account. There may also be several factors such as traffic policy that affect both air pollution and COVID-19 outcomes simultaneously. So not accounting for these factors would lead to omitted variable bias. And just like these 2 examples, there are actually several factors, confounding variables that we usually cannot measure, and not accounting for these variables would invalidate our analysis. So what we do to overcome this problem is we use a statistical method called instrumental variable estimation. And these, the underlying idea here is that in a first step, we isolate exogenous variation in air pollution by using an instrument. So in the COVID literature, 2 studies have taken this approach, and they have used 2 different instruments. One is wind direction, and the other one is environmental regulation. And these instruments affect air pollution. However, they are not in any other way related to COVID-19 outcomes. So in the first step, we identify exogenous variation in air pollution with this instrument, and then in the second step, we use this exogenous variation in air pollution to estimate how it affects COVID-19 outcomes. And this exogenous variation in air pollution is no longer related to confounding variables. Now, I mentioned that other studies have used wind direction and environmental regulation as an instrument. We use a different instrument in our study, and this instrument is a meteorological phenomenon called thermal inversions. And I will explain what this is on this slide here. You can see in this graph on the left side, under normal conditions, we have the temperature of the air decreases with altitude, and this means that air pollutants can disperse. When an inversion episode occurs, we have a layer of warmer air above a layer of colder air, and this essentially traps pollutants to the ground, such that pollution exposure is increased in these inversion episodes. using thermal inversions as an instrument to analyze the effects of air pollution on several outcomes is a well-proven strategy in the air pollution literature. Several studies have used this approach, and we are now the first to use this approach in the context of air pollution effects on COVID-19 outcomes. So how is our study set up? We compiled data for 6 different countries: Belgium, Brazil, Germany, Great Britain, Italy, and the US. So this is a geographically diverse set of countries, and we compiled data for the months January through April in 2020, because this is when we conducted the analysis. Then we estimate, or we implement our instrumental variable approach by using a fixed effects Poisson model. And the unit of observation in this model is the district. So we have a high spatial resolution in our analysis. We also have a high temporal resolution because our models are estimated at the day or week level. Now to conduct this analysis with this high temporal and spatial resolution, this is made possible by using data from the following sources. First, we use weather data from the European Center for Medium Range Weather Forecast. There's a data product called ERA5. And from these data, we obtain information on different weather conditions. And from these weather conditions, we can also determine whether an inversion occurs. Then we use pollution data. These are remote sensing data from the MODIS satellite from NASA, providing us with daily mean levels of aerosol optical death, considered a proxy for PM2.5. And here, these data come at a 1 kilometer resolution grid, and using this data allows us to have a consistent air pollution measure for all the 6 countries in our sample. Then we use COVID-19 data, which we scraped last year from web pages from official sources. These are government reported statistics. We have them for the 6 countries that I mentioned, but the death numbers we only have for 4 of these countries. And then last but not least, we also use mobility data from the social media platform Facebook. And we have data on government responses by countries, COVID-related policies. These are all registered in the Oxford COVID-19 Government Response Tracker, and we use these mobility and policy data to as control variables mostly, but also to conduct robustness checks in our analysis. So I will briefly summarize the key findings of our analysis. The question of interest is, does short-term air pollution affect COVID-19 case and death numbers? And in a first step, we isolate exogenous variation in air pollution by estimating the effect of thermal inversions on air pollution. This is the resulting regression table. Here we run regressions for different time frames and with different control variable sets. And what emerges from this table is that in our preferred and most stringent specifications is that an additional weekday with an inversion increases the average air pollution concentration by about 3.4 to 4%. And these results are very much in line with what other studies on thermal inversions in the air pollution literature have found. Now, in the second step, we then want to know how thermal inversion-driven air pollution affects COVID-19 case numbers and COVID-19 death numbers. And what emerges from the regression table here is, first of all, again, this is from our preferred and most stringent specifications, is that with every 1% increase in the average air pollution concentration, the case numbers grow by 1.5% approximately, and the death numbers grow by 5.1% approximately. So there is a greater effect on the death numbers than on the case numbers. And this indicates that death numbers do not only increase because the case numbers increase, but there also seems to be a change in the survival rate of the newly infected patients. Now we also look at the timing of the effects that we find. And before I show you our findings here, I want to briefly explain the hypothesis that we had on when to expect to see cases for someone who is exposed to pollution but is not yet registered as an infected person. So what you see here is a timeline in days. It shows the days after pollution exposure. Pollution exposure is here on the very beginning of this timeline. And now, given available knowledge about the average incubation time, about delays in testing and reporting, and about the average time or the time it takes to develop symptoms, this is not the average time, but the time where almost more than 90% of the patients develop symptoms, actually. So given knowledge about these factors, we expect that the effects should mostly lie in these blue shaded areas for with regard to the cases. With regard to the death numbers, we know that the median number between symptom development and death is approximately 18 days. So we expected that most or the strongest effects should be visible in this red shaded area. Now here you see the effects that we estimate when running a model on the daily level. The blue dots are days on which we measure statistically significant increases in the case numbers. The red dots are days on which we estimate statistically significant increases in the death numbers. And we can see that these effects do lie mostly in the areas where we would expect them to be. So what this highlights is, first of all, I should note that this illustration is, of course, a very rough illustration. We know that the course of the disease can vary substantially for individuals. So this is really just a rough illustration supposed to show where we would expect the strongest effects. But what it highlights is that, or it supports the notion that pollution exposure at the very beginning of the disease does seem to play a very important role in the course of COVID-19 infection. So I will briefly summarize the key takeaways from our study. What we do is we combine satellite imagery and COVID-19 data, which allows us to cover a geographically diverse set of countries at a high spatial and temporal resolution. And we expect that this analysis has a higher external validity than available individual country studies. Our results show that pollution exposure at around the beginning of the infection in the pre-symptomatic phase seems to be very important, and pollution does not only increase COVID-19 cases, but seems to also decrease the rate of survival among them. And we conclude that even short-term reductions in air pollution can help mitigate the spread and the severity of COVID-19 infections. And I will stop here and thank you very much for your attention.
Great, thanks very much, Hannah, for that data and analysis. It obviously has self-evident relevance to the challenges we're facing in Southeast Asia. I would like to ask from the side of the Secretariat, could you give us some detail on the methodology that your group used in the identification of thermal inversion conditions?
Yes, so are you familiar with the instrumental variable estimation approach?
Yes.
Okay. Yeah, so the identification of thermal inversions, we actually just follow the common literature. We are not the first to implement this or to exploit this instrument in an instrumental variable design. So we just follow other air pollution studies that have already implemented this. What we do is I explained we use data from the ERA5 weather data product, and it provides weather data on different temperature layers, and the construction or the calculation of an inversion event is basically then we subtract the temperature at the higher pressure level from the temperature at a lower temperature at a lower pressure level, and then we get a difference, and this difference in the temperature between these layers is considered the strength of the inversion that we use as an instrument. Does that answer your question, or?
Yes, thanks very much. I think that a similar methodology would be of great usefulness to us here, given that a number of our areas have very strong seasonal pollution patterns. Some have hypothesized that the presence of inversion events is the key factor in being able to predict those peaks in the observed patternicity of the PM 2.5 data in the area. So this is another aspect that would be very beneficial for us to be able to really determine when a pollution spike is caused by or influenced by an inversion or by increase or change in the source of the particles. So that's great. Thank you very much.
Yeah, I'm happy to provide more detailed information if that helps you in any way.
Yes, thanks very much. I think it's very likely that we will want to hear from you again on this. So thank you for that. So with that being said, if there are no other hands from the floor, I'd like to then proceed to our next presenter, Jay from Stockholm Environment Institute, who will highlight some policy measure issues. Jay, over to you.
Thank you. Let me just don't know if you can you see my screen?
Yes, you're good to go.
Awesome. Okay. So thank you for inviting me to present my research. So this particular research is in the form of a working paper that we have, and the name of the title of the research is to understanding the regulatory context. So the main focus of the project was to have to conduct a comprehensive desk review for Thailand's existing policy and regulations related to air quality and map out their interlinkages and identify the gaps, as well as identify the barriers and opportunities for policy implementation for the existing air quality policies and plans. Also, the intention of this project was to serve as a background to assist in identifying entry points for local and national policy recommendations. So just jumping straight to the results, since we all know what the basics of what are the sources of air pollution and all of that. So this was one of the results. This flow sheet was basically the methodology for my project was literature review as well as interviews, and the data collected from both have been presented in this particular flow sheet format. And in this flow sheet, we can see it's really detailed actually. So I'm sorry if you don't have time to see the entire thing, but in the key you can see the ones in the red are acts and the ones in the black are plans. So this is the air quality regulatory framework basically of Thailand, and the ones in red are enforceable, which are the acts, and the ones in black are non-enforceable. So they are mostly suggestions or recommendations provided by the government. Also, I have distinguished each of them the color in different colors to show which ministry has the authority over which plan or act. And as you can see, I have put in a bit of arrows. They are the only ones that are actually like interconnected or a subsection of the actual act. So if you can see here, there are like really less arrows in the entire sheet, which means that essentially most of these acts or plans have been enforced very individualistically or in silos. Why is that relevant? It's because most of the air quality work is suppose like it will be more effective if it is done in a very collaborative and a very national top-down methodological approach. But as we can see here, it's very siloed, and that reduces the impact of the air quality work or it just makes the air quality efforts very narrow or very focused to one particular sector. Like, for example, if the Ministry of Industry, you can see there are like 2 or 3 plans, they are very like specifically to a certain type of industry. So that is one of the conclusions that we came out of this graph. Also, I happen to map this policy mapping where we segregated the plans and legislations with respect to the sources of air pollutants. But they are basically all the boxes are from the previous graph as well. So in addition to the mapping and mapping the interconnections, we try to identify the barriers and enablers to policy enforcement based on different air pollutant sources. So with respect to agriculture, open burning, and energy, the barriers, these are actually, this is in a form of a very big table. These are the few main highlights that I have highlighted here, but there are much more points that are in the working paper. So the main highlights are, the main highlighted barriers to enforcement basically are insufficient air monitoring, which actually is improving with the number of like air monitors that have been implemented by PCD, but there's currently not enough air monitoring. There is lack of public awareness regarding health impacts of haze and open burning. Of course, there is a time of the year where there are all these news articles, media articles that talk about haze, mostly around winter, but there isn't much of like a constant awareness or the urgency of it, except for those limited time of the months of the year. There is slow, significant progress in increasing energy efficiency. The majority, this is another interesting one where majority of the Thailand's farmlands are leased, which leads to a lack of will and capacity to invest in alternative waste management practices to avoid open burning. And also inadequate and inefficiently implemented policies. Like we said, there are, like we saw, there are many policies that have been just set up, but they have not been completely implemented. So the second air pollutant source that we studied was vehicular emissions. The main 3 barriers for that was tax on older vehicles is lower than the new ones. That promotes the usage of older, inefficient cars with older engines. Urban areas are inadequately planned to promote mass transit and active transport. We have a very good mass transit system in Bangkok, but in other parts of the country, there isn't a very well-connected mass transit system yet. So that leads to a lot of course, a lot of using of individual cars and motorcycles. Also, the process of upgrading Euro 5 or 6 standards is moving slowly. I'm sure you know what Euro 5 and 6 is, but so Euro 5 was originally scheduled for 2020, but has now been pushed back to 2024. I think it was mostly because of COVID and all the other urgent things that the government had to face. The third air pollutant source was industrial emissions, and the main barriers are a lack of communication and public participation and decision-making processes for mega construction development projects. So that leads to in general lack of public awareness when it comes to these projects, and there is lack of public involvement when it comes to voicing an opinion on what are the industrial emissions when it comes to construction sites. Also, policy focus on higher economic growth. That leads to a lot of like growth of industrial areas like Rayong district, things like that. Shortage of industrial emission data collection and measurement due to lack of air quality planning, inadequate standardized monitoring measures, and lack of public participation in general in industrial air emissions due to lack of awareness or available data that is publicly available actually. And the last one was others, that were the overarching other air pollutant sources, which is the barriers are no clear enforcement of air environmental policies and insufficient number of governmental organizations involved in air pollution mitigation. Like you said, like you see in the graph, there are already a lot of ministries involved, but again, silos, and not all of the ministries are involved in the air quality in enforcing inequality policies. Of course, also no updated air quality standards. The last time they were updated was in 2010, which is almost a decade ago. So there is high need for doing that soon, and air quality monitoring and reporting is not yet comprehensive with limited monitoring sites like I mentioned, and a lack of any framework that enables multi-sectoral collaboration, of course, because of the siloed approach. Well, I did highlight a lot of barriers, but there are, of course, a lot of key actors that drive change. The main three key actors that we found out was collaborative efforts are needed between governmental and non-governmental actors. Up till now, I said there should be a collaboration between different governmental ministries, but of course, there should be that, and along with that, there should be non-governmental actors like civil citizen groups, NGOs, that should be able to voice their opinions much more effectively and should be heard and should be worked with collaboration in enforcing these policies and plans. The second one is civilian awareness. Measures should be raised through social media workshops throughout the year. Most of Thailand in general, we found out, was most of the citizens in Thailand have Facebook or the main social media. They have it on their phone, so it's really easy to raise awareness through Facebook and Instagram and the mainstream social media networks. And also involving local stakeholders like local communities, local governments, and local academics who have been researching on the topic to voice their opinion and participate in policy making. Of course, there have been a lot of efforts that have been done before, and these are the success stories that also we came across and we highlighted. The first one was the low sulfur regulation that is mostly, that is for shipping fleets that given like Thailand has a long coastal line and there's a lot of shipping and that goes on. This is a very important regulation that would create a lot of impact eventually. So the regulation that was implemented in, I think, 2020, and it's successfully being implemented, was to reduce the sulfur content in the shipping fleets, to reduce the sulfur contents in their fuels from 3.5% to 0.5%. And it's already in progress and it's successfully implemented. Another success story was collaborating cross-boundary monitoring. So Thailand provided mobile air quality measurement units to Laos, Myanmar, Cambodia. This is mainly to have a collaborative effort to manage cross-boundary haze pollution, transboundary haze pollution, and that has that collaborative and providing units and that collaborative work really helped in fostering cross-country collaborating efforts to combat transboundary haze. The other main very important success story was the two-stroke motorcycle engine phase out. In 1993, Bangkok adopted a regulatory method to encourage the use of four-stroke motorcycles through trade-in incentives, financial incentives, and as well as awareness raising workshops. Before 1993, it was mostly four-stroke motorcycles, which caused much more pollution in the form of carbon monoxide and sulfur dioxide. That was I think they were the most older ones that caused the most amount of pollutants. So they were, after the implementation of the phase out program, now in 2007, which is also not recent, but quite back, most of the four-stroke motorcycle, 100% of the, sorry, there's a grammatical error here, but 100% of the motorcycle engines are two-stroke. So that was one of the major success story with governmental and private sector collaboration. The other success story was Safe Schools in Khon Kaen. So here there is, in Khon Kaen, there is a lot of PM 2.5 pollution at a certain time of the year. So the municipality implemented a safe school strategy where when the monitor exceeds a certain level of PM 2.5, the classrooms are completely closed and they have safety equipment that in place that allows schooling to continue and students to breathe fresh air and safe air rather than shutting down the schools that was happening previously. And that is a very good success story that a lot of other schools can implement around the country. And that's pretty much it, all my results. And if you are interested in knowing more about the in-depth results and details, this is the link to the working paper. Thank you.
Thanks very much, Jay, for that informative presentation. I think obviously, as the bulk of the attendees today are researchers, being able to see a clear link from the science coming from that research to policy action, to produce actual results in PM 2.5 and related air pollution is really key. So this is one area that we've prioritized to strengthen and move forward. I'd like to open the floor now for any questions from the group on any of the policy measures that Jay has identified. While we have that time, our next speaker will be Dr. Lim-Sok Chang from the National Institute of Environmental Research, Korea. So I invite him to prepare to take the floor. And as he gets ready for that, Jay, could you let us know what you anticipate being the future direction of this research work?
So we have a few other specific projects that have been evolved from the base study that we've done. And two of the projects involve studying specific air pollutants and the vulnerability, like differentiated vulnerability impacts for different types of workers and informal waste pickers. So that is one of the things that have evolved from this baseline study. But eventually we are hoping that this study can provide as a sort of baseline to see, okay, these are the type of policies and this is what we can work on, and eventually help the other researchers to come up with more specific research questions and ideas.
Great, thanks for that. I think from the perspective of the Secretariat, one of the things we're trying to be very mindful of are the secondary impacts of air pollution. From the perspective of gender, for example, women employed in travel and tourism and hospitality industries are obviously more likely to have their livelihoods disrupted if severe air pollution events impact the employment in those industries and accordingly those households. So look forward to the continuing results from your work. So at this time, let's go ahead and proceed onward. Oh, I see Dr. Kim, your hand is up. Please go ahead.
Yes, thank you, Jay. It's very interesting presentation. Have you come across any like policy especially for children?
I'm sorry, can you repeat the question?
For children, so any policy specifically target children for reducing pollution?
Well, these, there hasn't been any actually. It's all, or most of the policies have been focused around largely those sectors that are very economically relevant. So that's industries or even agriculture. I have not come across any policies that do consider children as a separate entity, but there are definitely a lot of projects and researches that are going on that show the impact of differentiated impact of air quality towards children.
Okay, great. Thanks for that, Jay. I see we have a hand up from UNIDO. Suksiri, please go ahead. You have the floor.
Sure, thanks. Thanks. It's very comprehensive presentation in terms of, in particular, in terms of how you analyze the structure in terms of the air pollution policy making kind of agencies. My question though actually very basic, and then I do apologize for my ignorance. So the paper, is it about just PM 2.5 or air pollution in general, in Thailand in general? Because if it the air pollution in Thailand in general, I have a follow-up kind of a question.
Yes, it's about air pollution in general.
In general, right?
Yes. Yes.
Right. Then if it's so, I'm not so sure which state is your paper, but the box that you're showing, I think you're missing one box. Is actually just you pointed out, because it's so sectoral, and within Ministry of Industry there is another department called Department of Primary Industry and Mines. They regulate a special groups of industries, and they also regulate the air pollution that coming out of those industries. In particular, UNIDO, we work a lot on dioxins, which is regulated by the Stockholm Convention. So yeah, basically that very sophisticated kind of analysis of the policy making kind of agencies. You have missed one small box of one of the departments in Ministry of Industry. I can let you know kind of if the paper is still kind of amendable, but it's minor, but is that department actually has its own act, and then also regulates a bunch of these smelters, which is also emits these dioxins as well. We done quite a very intensive work on dioxins that emitted from these sectors. So I can give you more information about that if that would be benefit to your paper though, but if not, yeah, but if the paper is finalized, and that's fine. I think it's good as it is.
Yeah, actually the paper is already published, but I definitely love, for my personal end, I would love to know what I have missed, and I can probably reach out to you later and we can have a conversation. But of course, I know like I am researching, as I'm researching, I'm learning things too. So it's but natural for me to miss many things that I'm not an expert in. Of course, thank you for pointing that out. We can have a discussion after the event or anytime you are available. I could reach out to you.
Sure. And then one small point for the group though. I'm not so sure what is our intention, whether or not we're going beyond PM 2.5 or PM 10, but we do work a lot on dioxins, and I hope you are aware that Thailand house its own very sophisticated and perhaps most advanced dioxin lab in Southeast Asia. So just to flag that out, and then perhaps in future we can invite the expert from that dioxin labs to present to us, because they have such a very rich data, and their data are real time as well. Thanks.
Sure. Thank you.
Thanks very much for that, Suksir. I think maybe from a note from the Secretariat that in the focus of the substance for this research symposium has been very particularly on PM 2.5 and its components. That being said, of course, strategically expanding the scope of air pollution work to include broader spectrum of compounds is very much necessary. We do take note of your recommendation and we'll ensure that that is reflected in the meeting report. So thank you very much for that. In order to keep us on the time, if there are any further questions for Jay, please do submit them and we'll make sure that those are routed and the answers reverted to you. But at this time, we would like to recognize Dr. Lim Sok Cheng from NIER to please take the floor with his presentation. We have invited this presentation because of the potential for the GEMS satellite to fill many of the data gaps which were identified by Jay. So Dr. Limsok, please, over to you.
Okay, thank you. Yeah, thank you for inviting me. I would like to introduce to you the new kind of air quality measurement from the space. It is called as Geostationary Environmental Monitoring Spectrometer, GEMS. So today I would like to show some preliminary result of GEMS and then the plan of GEMS data release. So you can see the picture of GEMS launching, which was successfully launched last February 19th. Yeah, GEMS environmental sensor monitors spatial temporal variation of key air pollutants, which include ozone, SOx, NOx, formaldehyde, and then colloxar, which these two are the proxy of VOC, volatile organic compound, and aerosols. It has 10 years of lifespan, and it covers almost whole East Asia, from India, from the west, and Japan, the east, and part of Mongolia and a part of Indonesia. It has a spatial resolution of 7 by 8 kilometer, so it's close to kind of a in Korea is approximately similar to city size. Also, this satellite is geostationary, so it has a more measurement frequency than low orbit satellite. Basically, it has 8 times per day measurement. And then this bottom shows the timeline of our activities. It was launched successfully last year, and then it underwent an in-orbit test, and finally we complete in-orbit test last October, and we start to release some part of GEMS data, especially 8 products, and then we will open more data in this coming October. Yeah, GEMS. This table shows the baseline products of GEMS. Totally, it has 20 products, including ozone. Ozone has several sub-products such as tropospheric ozone, stratospheric ozone, and total ozone. And for example, aerosol, it has 4 products: aerosol optical depth, and aerosol index, and single skin albedo, so aerosol effective height. I think it's very important where the aerosol exists in the atmosphere. The GEMS also give information of height of GEMS aerosols layer, and it includes a VOC proxy, formaldehyde and colloxar, and then NO2 is the main pollutants from the car traffic or industrial activity, and SO2 and the UV index like that. This figure shows the image of the base GEMS product from AOD to surface albedo. You can see that the time evolutions of each product. It has hourly basis measurement of each product. Yeah, our GEMS observation plan is like this. It monitors air pollution in East Asia, but the coverage differs during the day. Usually in the morning, it covers half East and half Korea, and in the afternoon, it expanded into Central and to the West, including India. So this is a whole observation scenario from January to December. As I mentioned, in the early, usually in the morning, it covers east, and then expand its coverage to whole East Asia. Yeah, let me show some result, an example of GEMS product. This is a product of NO2, especially in Northeast Asia. You can see some hotspot in this region, Seoul and Busan, and some major city in China. The good thing is that it monitors the temporary daily variation of air pollutants. So you can see that where this product comes from, and then also where these products go or transported. So you can see that pollutions usually emitted from major city locally produced, and then diffused or transported in the neighboring regions. So we can see that if you pick up some places, you can see from this spatial temporal map of air pollutants, we can understand that where this pollutants comes from. This GEMS product has good correlations with existing low orbit satellite called as TROPOMI. This satellite has more NO2 concentration than TROPOMI, but has good correlations with the TROPOMI. So it means that the GEMS has a good performance, even though compared to low orbit satellite. As I mentioned, GEMS has an advantage of monitoring daily variations in urban scale. This shows some example of daily variation in urban scale in some cities, Singapore, Kuala Lumpur, and Seoul, Busan, and Hong Kong and Macau. I'm sorry not to show you the Thailand city, because you are less polluted than this city. So we can see that the temporal variations of these pollutants, it has a peak in the morning due to rush hour in the morning, and then goes down around the noon time, and then increase in the afternoon. So it shows the emission of car traffic in the urban cities. This figure shows the example of aerosol optical test which is related to particle matter. You can see that where AOD is high, and then aerosol, to what direction aerosols moves and to go. So in this case, you can see that the high aerosol pollutions in the desert area and major cities in China, and then it moves to the east along with the westerly wind. So we can understand that the long-range transport has a large impact on the local air quality in Korea. Also, it has we compared our product with other well-validated satellite, and we found that GEMS has a good performance. Yeah. It shows that the correlation. This figure shows that the correlations with the Gaussian satellite, and it has considerable correlations with the Gaussian. And this picture shows the one yellow dust event detected by GEMS, observed by GEMS, this figure shows that the time evolution, daily evolution of yellow dust. It was Asian dust occurred in the Mongolia area, and then moved to Shandong regions, and then arrived at Korea 3 days later. and then some part of yellow dust was depleted, was decoupled from the mainstream. So this branch in the southern China and moves to the east and then pass through Jeju Island and goes to the East Sea. So GEMS satellite had successfully detected yellow dust currents at the transport like this. Yeah, this is another base product of GEMS, SO2. Usually SO2 comes from volcanic eruption. So GEMS SO2 successfully detected the eruptions at the Enoshima Island in Japan. At the same time, global satellite probe OMI also detected this SO2 emitted from the volcano. But what is the difference between two is that GEMS can track the SO2 plumes in our scale, but probe OMI only visit this area once per day, so it can take a shot at one time. But GEMS can detect or follow the evolution of these SO2 plumes. Yeah, as you know, that the satellite always requires considerable resources for calibration and validations. This figure shows some result of GEMS validations during the August and October last year. All the basic product has a good performance compared with the low satellite. This shows the metrics of GEMS validations. You can see that the good performance in terms of correlations. Red colors indicate the achieved correlations, and achieved correlation, and the blue color is indicate the correlations. You can see that achieved correlations is almost within the goal correlations for all product. So we found that GEMS has a good performance as we expected. Oh, sorry. Yeah, I showed you the base product of GEMS, and then we had a research on the application of GEMS product. This is one example of GEMS data applications. AI-based PM2.5 estimation from GEMS AOD. As you know, GEMS satellite measure total amounts of air pollutants, but public is very interested in the concentrations on the ground. So we are using the AI technique to convert column density to surface concentrations. This figure shows one example of the conversion AOD to PM2.5. So it shows the high pollution of PM2.5 in the oceans. Especially over the ocean, there is no ground station. So this is only way to get the data of particulate matter of the oceans. As I mentioned, GEMS monitor spatial temporal variation of air pollutants. So it has an advantage to estimate how much aerosol come into a certain region and how many will exit at the certain regions. During these two informations, we can calculate it. The influx, we can calculate the estimation of long-range transport in specific regions. Therefore, we have three stages. And the first stage, we first identify whether there is long-range transport or not. We applied a high split technique to diagnose to make a decision on the long-range transport. Especially this day, air comes from southern China and northern China, so we can see that there's a possibility of long-range transport. And then we can estimate inflow and outflow at the certain regions. Finally, we get the amount of long-range transported air pollutants, especially in these regions. So this is a good advantage of geospatial satellite. Yeah, finally, I would like to introduce you the release plan of GEMS imaging. As I already mentioned, we already started GEMS data release. So some data already were released, and in the coming October, we release remaining of our product. So finally, we will, in this coming October, public can access aerosols, ozone, and cloud. Previously, is not available until this year, and next year we plan to release previously. But anyway, this year we NO2, SO2, UV. Most of GEMS base product will be released until coming October, I think. So if you are interested in it, you can easily visit our website. I didn't show it this year, but anyway, you can type the GEMS, so you can find our website. So if you go to our website, you can enjoy the GEMS imaging, some product, and in the coming October, you can more of GEMS product on the website. Thank you for your attention.
Thanks very much for that presentation. I hope it's evident the potential of this instrument for supplying some key data for the forward analysis and priorities for the group. I'll open the floor now for anyone who would like to pose any questions to Dr. Lim Sok Cheng. Okay, ADPC, please go ahead.
Hello, good afternoon. Thank you so much for this nice presentation. The GEMS data product, we're looking forward, and it will greatly advance the Earth observation capacity of Southeast Asia. I'd like to ask a technical question, and I noticed that in slide number 7, you presented the SO2 product of the GEMS and the SO2 product of the Sentinel-5P. And I noticed that in Sentinel-5P, there's a salt and pepper effect in the image, while in the GEMS product, the product looks more smooth. And how would you explain this difference in these two products?
Okay, I believe that each satellite algorithm used special profile informations, which comes from usually model, numerical air quality model. We use our own numerical model. The Tropomi group has their own model to get the profile information. So in terms of NO2, GEMS product usually higher than Tropomi because our profile is more updated compared to Tropomi numerical model. So it depends on what kind of input information is used to get the product. So I cannot give you exact answer to why SO2 has some difference, but usually it comes from what kind of profile information is used.
All right, I'm covered. Thank you very much for your answer.
Yeah.
Okay, great. Thanks very much. So I think at this stage, we will announce a change to the program. As has been previously published, we'd identified having 30 minutes for the Secretariat to review conclusions between 4 and 4:30. However, given the richness of the findings that have been shared and the remaining discussion which we are likely to have, we will provide an expanded outcomes document, which we'll circulate to presenters after the fact in the next coming days, so that we can ensure that everything has been properly captured. Therefore, at this point, I'm happy to take the floor to talk a bit about the state of the Secretariat's air pollution work with data science in Chiang Mai. So I'll go ahead with that material now, and then open the floor for questions and comments. Okay, so as I'd mentioned previously, when we took the floor on health, we have been able to create a data warehouse on air pollution data sets from Thailand, and to provide the further information that had been requested, we'll now illustrate what we've done and how we've done it. So for this slide, with relationship to the PM 2.5 measures that Dr. Kim asked about earlier, this is a visual showing the data points that we have been tracking for the city of Chiang Mai. Obviously, and thanks to the earlier presenters for illustrating the growth in PM 2.5 stations, the completeness of data, and so forth. You know, all of us who work with these data sets know the historical problems and the trends that the instruments have reported to us. So we all need to deal with this issue. Similar to the approaches used by previous authors, and drawing on the strong correlation between PM 2.5 and PM 10 measurements, we have constructed analytical models to be able to fill the data gaps which have been present to ensure that we're getting reliable measures of PM 2.5 for the purposes of these exercises. So this shows you what we have in terms of readings for the particular year series for these compounds. When it comes to putting those all together, we have the patternicity, which emerges, clearly indicating the seasonal nature of PM 2.5 pollution for Chiang Mai. This scatter plot shows the consistent nature of those seasonal factors among and across the years in question, which facilitates the modeling exercise for the data quality issues. As we put those together, this is the performance metrics for the model itself. We've used random forest in order to model and predict the PM 2.5 measurements, and this has allowed us to predict quite reasonably the levels necessary. As we look into the inferences and the errors present in this data stream, I'd like to provide this visual showing where the confidence intervals are for the observed data and which data design decisions we've made in moving forward with the Chiang Mai air pollution metrics. Now, one emerging point that I think is clearly shown in the patterns that we have here is the significance of the meteorological factors that influence particularly spike conditions when we have elevated pollution levels resulting in high incidence. Obviously, we've heard yesterday from the other authors on the influence of wind conditions and thermal inversions. So we also share that view. So with that understanding of the methodology that we've used in applying data science to the situation in Chiang Mai, I'd like to move forward to what the results have shown and where we've gone with those. So this is a quick visual on the trend lines in the seasonal nature of the air pollution in the municipality of Chiang Mai mapped to the number of hotspots observed through the MODIS and FEARS data sets in the surrounding area. Now, in really understanding the context of biomass burning, it's necessary to break this down. Obviously, the distance and the transboundary nature that we have of these factors bears careful consideration. So when we start breaking this down geographically, we can see that the proportionality of fires and their distance from the municipality of Chiang Mai is a key issue in those distributions. So in an effort to further understand that, we have also disaggregated the observed hotspots by country. And in the context of this analysis, it's very important to consider not only the count of the fire hotspots, but the burning activities per square kilometer in the neighboring countries, which really helps illustrate the nuances of this question. Now, when we talk about biomass burning, obviously we have key aspects in forest fires versus agriculturally relevant fires, fires that are man-made, anthropogenic, and the research that we heard of yesterday in looking at the chemical profile to determine whether or not it's a leaf-based fire or if it's rice or straw, sugarcane is really important. Obviously, we don't have that nature of chemical profile data from satellite observations at this stage for this time series, but we are able to identify particular locations which have repeat burning incidents over the time series that we do have observations for. It's reasonably probable that a sequence of fires in the same location across burning seasons is suggested of an anthropogenic factor. This is a proxy variable, and when we consider this nuance in the data, it's very intriguing to determine which areas are most likely to be prioritized for interventions in man-made fires. So taking all of these factors into account in the relationship of biomass burning and PM2.5 for Chiang Mai specifically, it makes it possible to accurately model and predict the impact of policy-based interventions on the end AQI that would be experienced by residents of Chiang Mai. The animation that we have on the screen here is showing how that model would project the influence of no-burn policies on the air quality. Certainly, given the track record thus far and the policy efforts that we've seen, even significant reductions of biomass burning in a comparatively smaller radius around Chiang Mai has not been successful in reducing the total AQI to healthy levels. Our model is very consistent in reinforcing the need for an integrated transboundary regional approach to reduce biomass burning collectively throughout the ecosystem in order to really close that gap. There's not one single point on the map that can be exclusively responsible for all of those AQI emissions. It really has to be integrated and regional in order to make the difference that is necessary to achieve healthy air. A further example of this effect can be seen when we apply these observations to Korat. This is obviously significantly to the east of Chiang Mai, and we see clearly in the data patternicity when compared over a time series that the seasonal effects of AQI for that location have a very high correlation to the agricultural burning seasons in neighboring ecosystems, emphasizing the collective nature and the need to integrate efforts to actually deliver improved air quality in these types of areas. So with that insight in the methodology and findings that we have in our existing draft, we think that this reinforces that at the national level, that the top three sources of air pollution for Thailand are very likely to be agricultural burning, vehicle emissions, and industry and power generation. Based on an urban level perspective and a really customized analysis to particular locations, it becomes very clear that the sources of air pollution for a particular point of the map can vary significantly among and between particular cities. Therefore, it's really important to take that urban level analysis and capture the nuances of what's happening in a particular location. The primary driver of air pollution for Chiang Mai is not going to be the same as the primary driver for Nakhon Si Thammarat or cities with less impact in biomass burning and different geographies. Therefore, it's our view that misattribution of air pollution sourcing is unfortunately likely when national level averages are applied to specific locations without taking a customized approach to understanding the sources. With that being understood, our view of where the science is leading is that we have a clear need to be able to accurately calculate the emissions and pollutants by agricultural sectors for the air quality compositions in Chiang Mai. Following that calculation, the policy actions should address each one of those specific outputs in a sustainable manner. So for those findings to be translated into action, we think there needs to be collaborative coordination between the private sector, national government, and the United Nations role in order to be able to bring the stakeholders to the table to properly take the targeted action necessary for the specific conditions with which exist. In this regard, I'm happy to mention that there has been some really positive forward action from the UN Global Compact network in Thailand, with strong support from private sector actors in adopting more sustainable practices and actively becoming part of the solution. So this is the perspective of the Secretariat on what data science can tell us about the drivers of air pollution for Chiang Mai and the need for customized and coordinated approach in order to really bring down the levels of air pollution for the citizens. So thank you very much for your attention on this, and I'll now open the floor for any questions or feedback on our methodology. Thanks. Okay, thanks. See some hands going up. I hope I'm getting these in the correct order. I think Kun Somporn, you have the floor first, and then we'll go from there. Thank you.
Okay, thank you very much, Matthew, for this informative information that we have got. But I still doubt about your conclusion. Could you please go back to the slide of your conclusion about the source of pollution? Yes, for the top 3 sources, and you have mentioned agricultural burning as the major source rather than open burning, both in forest area and agricultural area. Do you actually overlay the land use with the 5 hotspots, or how you get this information?
Thanks very much for that question, and that's well noted. It may be advisable for us to change the language on this slide. We are using both level 2 and level 3 land use classifications to overlay with the burning data. I did not include that slide in this presentation, but maybe in a couple of minutes I could pull it up for you. So this is what we would see for the national level average, particularly for points of observation in the north, such as Chiang Mai. The forest burning is really a very major issue. And that nuance really needs to, as pointed out by myself, we can't speak, if we speak in the national level generalities, it really hides the local truth. And certainly for North Thailand, forest sourced open burning is a very key contributor. So very much agree. Thank you.
Okay, thank you.
Therefore, if I have the speaker list correctly, it's NIER and then Dr. Kim. Go ahead, NIER, you have the floor.
I think it's Lim Xiao.
I'm not sure if there's a technical issue there. Dr. Kim, since you're ready to go ahead, why don't you take the floor, and hopefully we may hear from NIER later on.
Thank you, Matt. It's very informative presentation, and I like it. Just a comment rather than actual question. The meteorological condition in Chiang Mai especially would be very challenging for any statistical model. So, and then you mentioned about that in your presentation. You have any way to go ahead with that? I mean, in machine learning?
Yes and no. This is a very key point. We have examined the impact of wind direction together with climate, temperature, and humidity in the data grid that we've applied into the random forest model. So we do identify that this is a key area, and those are the things that we have applied so far. We do see statistically significant relationships on things such as wind direction, for example. So that's the part where I would say the answer is yes. The part where I would say that the answer is no is that I think the key issue on all of our minds is being able to robustly and systematically integrate thermal inversions specifically into the model. And when we look at where our mean squared errors are, for example, and things like this, it's very suggestive that these spikes tend to be caused when very specific meteorological conditions come together. It's certainly my hope that together with the remote sensing and applications promoted by Dr. Hanna, for example, together with broader deployment of low-cost sensors, would really fill the data gap to take us to the next level on that. But in 2021, where we are now with the data, I think beyond wind direction, it's difficult to become more specific on the meteorological effects.
We earlier also investigated the meteorological pattern in Chiang Mai that induce burning and then high pollution level. We published a paper in Stockholm back in 2013. I can share it with you. We classify the meteorological pattern, synoptic pattern, into 4 patterns and try to investigate which pattern is more like with higher frequency during the burning period when it dry, because it's interrelated. When it dry, it burn more. So it's not only meteorology, it's meteorology and that. And then we try to classify in 4 patterns. So I hope with machine learning we can recognize that pattern easier, because our approach would use the like visual examination of the pattern for 10 years. I can share with you the paper we published earlier. And we found when we overlay the hotspot and the land use, we found that 80% of the hotspot appear in forest area for Chiang Mai. Only about 20 in that. And also share Ajahn Somporn question earlier. Is it Chiang Mai or northern provinces in Thailand have very high impact of forest fire, more than agricultural. Although they are interrelated, I guess. Many of agricultural fire actually catch the forest and cause the forest fire. So the root cause of the fire need to be actually identified in order to formulate the policy. Thank you. This is a big topic. I understand. So within a few minutes, I don't think. Well, we can talk about that later. Thank you.
Yes, I think maybe we could have a whole session or maybe even a whole event just on these issues, which are very important. Absolutely agree with your input and would very much welcome the submission of the analysis that you mentioned, as well noting, for example, some of Dr. Siwat's research on the impact that humidity and precipitation have on reducing the, removing certain compounds and particles from the chemical transportation. So it becomes really, there's a lot of interrelated factors there, and definitely enthusiastic to move forward with the meteorological monitoring that you're mentioning. So yeah, let's definitely do that. Thank you very much for that. And additionally, maybe we should have a whole session just on this. As part of the analysis that we've done, I'll just mention verbally, is also the land use data within Thailand, but also looking at the transportation of the PM2.5 from the neighboring countries into the stream of particulates, which then can accumulate over Chiang Mai for various reasons. So we really want to have the forest fire data and anthropogenic agricultural open burning collected and properly analyzed for the neighboring countries, as well as for the research conducted on the borders within Thailand. So we expect to be taking that forward from the UN side. So I hope I spoke to all of the points that you raised, Dr. Kim. Please let me know if I left anything out. So we're coming up on about 4:20. So if there are any other questions or concerns from the floor, please let me know. Bert, over to you now.
Thank you very much, Matthew. Also, thank you for the other speakers. It's all very good, very interesting. But I guess you're right. Maybe we need more time to discuss your results. But this very interesting point raised on agricultural and open burning, I guess that is very important, especially when you overlay the maps. Although logically, for us who live in Bangkok, we know that every year, November to March, November to February, when open burning or agricultural burning happens, that's when we face these very high levels of air pollution. So to our minds, definitely there is a link, and agricultural burning together with open burning is the major source. I'm not sure if you can say that at the national level all the year round, so I think we need to see your data as well. Because, for example, in the south of Thailand, in Bangkok, during these not cooler months or the hot months, from April to August, we don't really face a lot of air pollution or that levels of air pollution, but there is still air pollution, and you can say even that it's still high. And many have seen it again during the initial lockdowns that we faced. Like even if it's not the time of open burning or agricultural burning, there was still a decrease in air pollution in Bangkok due to the lockdowns. So again, those need to be looked at. It would also be good to see the results of the machine learning, this random forest model, to see it against the actual levels that are monitored. For example, I'm sure there is air quality data from the government in Chiang Mai or other parts of Thailand. They have a robust air quality monitoring network after all. So it would be good to see how it differs or what are the differences. And I think it definitely would be good information for all of us. I think all for now, Matthew, but thank you again.
I'm starting to lose track of my buttons. I have too many screens. Thank you for that, Bert, and absolutely very much well noted. I think that would be a fruitful direction for the next event to really focus the science on this question. There's a couple of points brought up there, and I hope I'm capturing them all. Number one is that, yes, the data I've shown here is specific to Chiang Mai. I would not want, it would be not scientifically valid to extrapolate the Chiang Mai analysis directly to the national average. And quite frankly, I think there's a very compelling case that we really should not be talking in national averages as much as possible because of the significance of the urban level perspective. So none of this should be viewed, none of the charts and the data that I've shown should be viewed as Thailand overall. It's specifically Chiang Mai. I also am wondering if I should pull on some of the other visuals, which very much reinforce your second point, Bert, on how much it changes from city to city. When we look at specific examples such as Nakhon Thammarat, there isn't a strong seasonal aspect to the observed air pollution in that city. And that is very clearly because their ecosystem has different exogenous factors. So it really has to be the city-centric perspective. We have not put very much Bangkok-specific data in the Secretariat's presentation, but would identify that as an area for future meetings. In terms of your specific request to put the prediction of the model next to the observed data, that I do have this slide on, so I can show you that right here and now, which is this visual where we have the data series from 2011 to 2020, and the highlight in green is the training data. The highlight in red is the portion where we hid the measured value and had the model predict what it expected it to be, and then compared the two. And that's where we get the R squared of 0.78 on the predictive capacity for the model for Chiang Mai. And then the further drill in on the distribution of the errors and why those would be, with an emphasis on the meteorological effects. So I really think that I would certainly love to have this level of truthing, showing of work for any city-specific analysis. And we certainly hope to be going in that direction with all of the cities that we're going to be working with. So I hope I captured answered all of the points that you raised, and we definitely take note of those observations for the focus of future sessions. I think particularly the impact of COVID mitigation measures on traffic and the relationship to observed air pollution in the context of thermal inversions. I think we could have a whole symposium just on that, very, very usefully. So thank you. Okay, I think we've got I've addressed all of the hands. It's 4:24, and I don't want to keep people late. But if anyone has any final points, don't hesitate to raise your hand. I would just like to thank you all for the contributions of your research and findings. It's extremely helpful for ESCAP in determining our paths forward, and are really very thankful for the insight and research that you have all provided. So thank you very much for your active attendance and participation, and we will be happy to circulate the draft findings for your consideration in the coming days. Thank you very much.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Thank you.
Okay, thank you.
Thank you.